The only questions you have are on those that use formulas, not on any concepts. Okay, so let's look at what we have. Question number 4 is frequency to wavelength. Question number 4 in the EPPs is frequency to wavelength. We've got frequency to energy, wavelength to energy, and energy to wavelength. Okay? Yes, sir.
So what was the thing that was extra credit for the test?
The review questions, the easy ones.
That was what I did yesterday. I'm thinking it was extra. Thinking it was extra package problem.
Okay. So you turned that in
I turned it in
yesterday? Okay, I haven't corrected it.
today. I turned it today.
Okay. Okay, I'll have that for your, if you want to have that be your final answers, but I'll take your review questions. If you've already turned them in, I'll use those. If you turn in review questions tomorrow during the exam, I'll consider the review questions for extra credit on the exam.
Okay.
That's the deal. The practice problems were due yesterday. The EPPs are due today. If they're not turned in, you can turn them in tomorrow. Okay? But tomorrow's the end of the grading period. All right. Was that or answer your question? Okay. So, do we have every case that, let's see, those 5 questions, yeah, those are the 5 different directions. So we're given frequency in 3 of them, we're given wavelength in 1 of them, and we're given the energy in the last one. Okay. Okay. I will when we work the problem. Yeah. All right, so question number 4 from the practice problems, it's the same exact type of problem as question number 4 from the EPPs. Anybody have a preference? Let's go ahead and do the EPP one, because it's the same problem. Okay? So, and I think we did that one already. So, frequency of a waveform. The frequency is 6.15 times 10 to the 14th hertz. What is the wavelength? Okay, what is the wavelength? Remember, we have 2 formulas so far, or two formulas in this module. The way I've written them is C is equal lambda F, and energy is equal to HF. You can also, because you can rearrange the speed of light formula, light is equal to lambda F, you can rearrange that for F, saying that F is equal to C over lambda, so you could also write the energy equation as HC over lambda. Same thing. In this case here, we're given frequency, we're given lambda, or excuse me, we're looking for lambda, and we need a formula where we have all but one of the variables. Is there anything mentioned in here about energy in this problem? No. Other speed of light, lambda, frequency. Do we have all but one variable? The one we're looking for is lambda, the wavelength, and we know C, it's a physical constant that never changes, and frequency we're given. So we have all but what we're looking for in that formula, so we use that one. So C equals lambda F. Now I'm going to rearrange the formula algebraically so that I have whatever I'm solving for all by itself on one side of the equal sign. Okay? Well, I want F to be all by itself, so I need to get rid of everything that's not F, right? So if I divide by lambda on both sides, the result is frequency equals C over lambda, just like I wrote right here. Okay? Because lambda will cancel lambda, and you're left with frequency equals C over lambda. But you were right. I messed up because we need to get what we're looking for all alone. I locked into frequency, but you were right because what we're actually looking for is lambda, right? Our unknown is lambda. So you're right. We need to solve this equation for lambda. Get lambda all by itself on one side of the equal sign. So to get lambda all by itself, we need to divide by frequency. Lambda equals speed of light divided by the frequency of the wave. Now we have our unknown variable all by itself on one side of the equal sign, and all the variables which we have a value for that we can plug in on the other side of the equal sign. You'll be given, but by now hopefully you remember that the speed of light is 3.0 times 10 to the 8th meters per second. All that divided by your frequency of 6.15 times 10 to the 14th hertz. Now, in terms of units, what is the actual? This is the unit of hertz is actually a common name for what units? A hertz is also known as a 1 per second. So just for units' sake, let me just change this now to be a 1 per second. Because my pattern is to go ahead and check to see if my units are, if my setup is right, my units of my answer will be right. In this case, wavelength is a distance unit, right? How long the wave is, it's a distance. So my formula, once I do the work, should leave me with a distance unit at the end. In this case, I've got meters per second over 1 per second. I'm hoping that this results in meters being all by itself. So if I just look at the units, I have a meters per second divided by a 1 per second, but to divide by a fraction is the same as to multiply by its reciprocal. So I'm going to multiply seconds per 1. See that? I take the numerator and write it. I take the denominator, I flip it, and then rather than dividing, I multiply. Same thing in math. Dividing by a fraction is the same as multiplying by its reciprocal. So in this, I can see my units are going to be seconds, cancel seconds, and I'm left with meters. It's a distance unit. So my setup is correct. Now I'm going to go back and actually do the math. Again, if you use a calculator, you just punch it in, hit the button, and mindlessly write down the answer. But if you made a finger mistake, you did something wrong in your setup, you don't have a way of really checking to know if your calculator answer is right or not. So what I like to do is do an estimate. I'm going to look at this and first of all look at the coefficients of my scientific notation right here. As I look at those coefficients, I see that I have 3 divided by 6.15, which is virtually 3 divided by 6, right? So what is 3 divided by 6? It's 0.5. It's a half, right? It's a half. But since this is a little bit bigger than 6, I'd expect it to be a little bit smaller than 6, not by much. So I'm going to say 4.8. Okay, what is it actually then? 4.9, okay. But we'll say right now it's 0.4, okay, 0.49. I knew it's just a tad below half. So I'll leave it in that form right now because 3 divided by 6 is a half. But it's a little bit less than a half. Now let's deal with the scientific notation portion. Times 10 to the, now we do scientific notation. When we divide by using scientific notation, what we do is subtract the exponents. When we multiply, we add the exponents. But when we divide, we subtract the exponents. So we have 8 minus 14. You subtract the denominator from the numerator. Okay? That's going to give me 0.49 times 10 to the negative 6. But I need to put it in proper scientific notation now. This becomes 4.9 times 10. Now when I went from 0.49 to 4.9, I made it larger. Do you agree? Yes. I made it larger, which means I need to make my exponent smaller. I made it larger by moving at one place, so I I made it larger by moving one place. I need to make this smaller by moving at one place. I need to move it more negative than it is now. It's at negative 6. It now becomes negative 7. Excuse me, meters. Not unless you're told to. But if we were told to, convert it to nanometers.
And how would,
Problems like this, are you always gonna make the exponent smaller?
You mean when we move it? It depends upon the direction you move it. If our answer here, for example, was 49 times 10 to the negative 6, I'd have to move it to the left to make it 4.9. So I would have made the number smaller. Therefore, we need to make the exponent larger. It all depends on the direction you move the decimal point.
so why couldn't you just leave it as 0.49?
This is improper form. Scientific notation always has one digit, decimal, and then the rest of the number. Okay. So if we wanted to convert this to nanometers, remember what is a nanometer? On top of your test and everything, a nanometer is a 10 times
Negative 4.
10 to the negative ninth. 10 to the negative ninth is nanometer. So let's just go ahead and say I'm going to have to rewrite this times 10 to the negative ninth meters. Let's just start with that. I have 4.9 to the negative 7. I want to make it something to the negative 9. Ma'am? So I'm taking, let's think about it the other way. When I go from negative 7 to negative 9, am I making that larger or smaller? From a negative 7 to a negative 9. I'm making it smaller, so I need to make the coefficient larger, right? You see that? To go from negative 7 to negative 9 is to make it smaller, so that whatever's in front has to be made larger. I make it smaller by effect by 2, right? From 7 to 9. So it means I need to move the decimal here to make this larger 2 places. So if it was 4.9, I'll put some placeholders here, and it now becomes 1, 2. But because of significant figures, it stays just simply as 490. So if you're asked to give the answer, what is the wavelength, you could say the wavelength is 4.7 times 10 to the negative, 4.9 times 10 to the negative 7th meters. If the question said, what is the wavelength in nanometers, your answer would be 490 nanometers. Because it's 4.9 times 10 to the negative 7th meters. To be a nanometer means I have to put it in times 10 to the negative 9th form. So then I can alter the coefficient, make it whatever I need it to be, times 10 to the negative 9th. All right? So this is just a straight light equation. You knowing the speed of light, given the frequency, solving for the unknown, which is wavelength. Everybody comfortable with that? Any other questions?
So will we have to know the equation, like the speed of light, frequency, or will it give it?
No, no, I'm not going to give you the formula.
So we have
No, you have to know these. These are troublesome. You have to know these two formulas, but you will be given the speed of light, and you'll be given Planck's constant when you need it.
Okay. Like the 3 times 10 to the 8 that would give us to that.
Yeah, you'd be given this, and you would have that from the problem. So everything you have here, this whole thing, the only thing you'd have to have memorized is the formula. C equals lambda f. And then know how to rearrange it for whatever you're looking for. Is there another question on this problem? Okay. Yes? I don't, but Mr. Parker apparently does. So here. This is my borrowed classroom. I'm only here for first period, so this isn't really my room for anything. Yes?
Under the box,
Mm-hmm.
is that 499 times 10 to the negative 9?
490. Mm-hmm. Times 10 to the negative 9th. And once you have it in the form of times 10 to the negative 9th, then you can replace times 10 to the negative 9th meters with nanometers. Okay? Get it all out. Let's go. Isn't there always? All right. So we comfortable with the given frequency going to wavelength? That's what we just did. Okay, frequency to wavelength. The next questions on here involve the energy equation, right? Because energy, they're looking for energy. So we're either going to be energy equals HF, or energy equals HF and the light frequency, C equals lambda F. You're either going to need this formula or both of them. First thing to do is look over and say, am I given frequency or wavelength? Hey, in this first one, I was given a frequency and asked for the energy. Okay. So if I'm given frequency and asked for energy, I only need this one equation right here. On the second question that you've asked to go over, we're given the wavelength, and we're asked for the energy. Now, we don't have a formula that uses wavelength and energy in the same formula, but we have two formulas that'll get us there. So this is a two-step problem that's just like this first one once you get past the first step. You have to go from wavelength to frequency, and then from frequency to energy on this one. See that? This first one here, on the first one we're given frequency, we know Planck's constant, and we're solving for energy. We got everything we need for that first one. On the second one, we're given wavelength. So we've got to go from wavelength up here, wavelength, and we're solving for frequency. So we're going to use frequency equals C over lambda on the second problem to solve for frequency, because we need to work energy in terms of frequency. And we know that wavelength and frequency are inversely proportional. Right? When one goes up, the other one goes down. So there's a constant that holds them together. They're related to the speed of light. So given wavelength, we can solve for frequency. Knowing frequency, we can solve for energy. I'm going to go ahead and do it as a two-step process. For those of you that get the math and get the concept, if you choose to alter your formula to this, more power to you. I think this is more direct and straightforward if you understand what you're doing. If you're still struggling with, am I doing the right thing? Just think, okay, figure out the frequency. Once I have the frequency, then figure out the energy. If you don't have frequency and you're asked for energy, you're going to have to get the frequency first. So let's go ahead and start with the second problem, since it includes the first problem as part of it, okay? When we do the first half of this problem, we will have done a problem exactly like this. And then the second part of this is common to both of them. Let me see if I said that the right way. I did not. When we do the first part of this, that's the unique part. And then we do the second part of it, it's the same as the one above it. Let's just go through it. Doing number 6 from the EPPs. It says a wave has a wavelength of 1.95 times 10 to the negative 7th meters. For now, yeah. Because number 5 is kind of embedded in number 6. It's not the same exact numbers, but how to do it is we're going to show you how to do it. See, in order to do number 5, we have frequency. For number 6, we have to first of all get frequency. And then once we get the frequency, from then on, they're both the same. So wavelength equals 1.95 times 10 to the negative 7th meters. Eventually I have to solve for energy, so I know I have to get frequency. So from this, I have to get frequency somehow. So I'm going to use this formula right here, that the frequency is equal to the speed of light divided by lambda, which is equal to 3.0 times 10 to the 8th meters per second divided by 1.95 times 10 to the negative 7th meters. Okay? This you'll be given, but it's a constant. We should know it by now. This one is unique to the problem. And because this unique wavelength is present, it's going to give us a unique frequency. So you plug it in your calculator. Me, I'm going to ballpark it by looking at the board. And it's going to be approximately, I'm going to write approximately, you're going to write equal to. I've got 3 divided by just a little bit less than 2. 3 divided by 2 would be 1.5. But it's a little bit more than that because that's a little bit less than 2. So it would be about 1.5, maybe 1.6, 1.5, okay. So it runs to 1.5. Let's say it's 1.5. Then I'm going to do my exponents times 10 to the... Now again, when we divide exponents we actually have to subtract the exponent. What I mean by that is times 10 to the what? The numerator, which is 8, subtract the denominator, subtract the denominator. The denominator is negative 7. So 8 minus a negative 7. Subtracting a negative is the same as adding a positive. And that's 1.5 times 10 to the 15th. Times 10 to the 15 hertz. Okay? And I can see by looking at it that I've got meters per second divided by meters. The meters cancels meters, and I've got 1 per seconds as my units, which are hertz, so we're good. Okay, so that's the frequency. We're asked for the energy given the wavelength. We can't get there with the wavelength. We first of all have to compute the frequency. Now we have a frequency to work with. Now from here on, problems 5 and 6 are basically the same. They're the same setup with slightly different numbers. So we're going to solve the second part of 6, knowing that it looks like, without the same numbers, but it looks like and flows like exactly like number 5. Okay, so we have a frequency, and now we're asked for the energy. Our energy equation, energy equals HF, Planck's constant times frequency, which we have. Planck's constant, 6.63. Do you have it there, Serena?
Yeah.
34? Okay. Just want to check because sometimes I get the exponents wrong. Now, just for fun, would you read off the units for Planck's constant there? Do you have that in front of you? Right, joules per 1 per seconds. Makes sense because when I multiply it by the frequency we determined was 1.5 times 10 to the 15th hertz. When I take joules per hertz divide and multiply hertz by it, what are my units? See that? Hertz cancels hertz and I'm left with joules. I'm asked for the energy, and joules is the energy unit. The setup is right. Now I have to actually do the math.
So you always get 6.62 like they give it to you?
Yeah, H, Planck's constant, will be given to you. This is the value you'll be using. 6.63 times 10 to the negative 34th. And again, I'm doing this without my answers or anything, so I wanted to make sure I didn't write it down wrong. 6.63 times 10 to the negative 34th. Now let's go through, and you would, again, on your calculator, punch in the numbers. I'm going to write down an approximate. It's 6, maybe 6.5 times 1.5. 6.5 times 1.5, 6.5, 3 1/4, 6, 9 3/4. Somewhere around there. So I'd say about 9.75. A little bit more than that, 9.8 maybe. 9.9. Okay, so I'm within a tenth. Now let's look at exponents. Times 10 to something. Remember, when you multiply in scientific notation, you add the exponents. So this would be a negative 34 plus 15. So let's say it's 9.8 times 10 to the, you got negative 34 plus 15. So we're left with negative 19, right? We're at think of the number line. We're at negative 34, and we need to make it 15 more positive, which means move it to the right 15 from negative 34. So negative 33, 32, 31, you count it up towards 0. So that gives us negative 19. So 9.8 times 10 to the negative 19th, and the units are joules. You would get that from the math. Hertz cancels hertz to leave you with joules. Also, since you're looking for energy, confirmed because joules is the energy unit. This problem right here, number 5, the only difference would be, rather than figuring out what frequency is, they already gave it to me. So then all I would do is stick that in here. 7.05 times 10 to the 14th would be in here, multiply them together, and that would be my energy. Okay. So if given frequency, looking for energy, just plug it in the equation. If given wavelength, convert the wavelength into frequency, and then plug it into the equation for energy. Questions on the energy equation? Because this last one is just a little twist on the energy equation. given the energy, solve for wavelength. Okay to erase? Right. Now let's just logic this one through before we throw any numbers at it. I'm given energy, and since we only know one energy equation, I know I'm going to have to use E equals HF in some way. I know that's going to come into play because I'm given energy, and I know Planck's, but I'm asked for wavelength. Can I solve for wavelength from this equation alone? No, but I can solve for frequency, and I know that I know that I know that I know if I have frequency, I can figure out wavelength. So from here, I can figure out frequency, and then from frequency, I can figure out wavelength. So this problem is like number 5 and number 6, backwards. Energy equals Planck's constant times frequency. If I'm looking for wavelength, I go, okay, but if I had frequency, I could figure out wavelength, but I can solve for frequency. So let me solve for frequency. Frequency is equal to the energy divided by Planck's constant. Okay? This is what I'm looking for, and these are things that I've been given. So I can solve for the energy by doing the math. E equals 1.50 times 10 to the negative 18th joules. That's my energy. And Planck's constant, we just said, was 6.63 times 10 to the negative 34th joules per hertz. Okay. So, again, you plug it in your calculator. We'll get it together on the board. 1.5 divided by 6.5. So 1.5 is about, it's going to be a little bit less than a quarter. Mm-hmm.
Does that say to the third?
34th. Yeah, cut it short. Thank you. Well, 6.63 times 10 to the negative 34th. So looking at the first part of it here, it's going to be a little bit less than a quarter. For my, what, 2.3? Something like that?
That's 2.3. Do you have to have 3 significant figures, or can you just have 2?
Written like this, well, this is defined as, so it's going to be 3 in this case, because we've got 3, even if we didn't, we looked at it, 3 and 3, the minimum would be 3, so 3 sig figs. But we said it was a little bit less, 0.23, so 226, 0.226. Now we're going to do the exponent. Remember, again, when you divide by using scientific notation, when you divide, you actually do that by subtracting the exponents. So it's going to be times 10 to the numerator is negative 18th minus the denominator. The denominator is negative 34th, so it would be minus a negative 34. Subtracting the negative is the same as adding a positive. And so that equals 0.226 times 10. That's a 6. 0.226 times 10 to the 16th. Positive 16th, right? Let's put it in proper form. 2.26 times 10 to the 15th. I made this one larger, so I need to make this smaller. Units, joules per hertz. My units there are hertz. Frequency, hertz. Okay, we're good. So 2.26 times 10 to the 15th hertz. Now that I have hertz, I can go for what I've been asked for. I've been asked for wavelength. So I keep pressing on. Speed of light equals lambda f. Trying to solve for lambda. Lambda equals frequency divided by speed of light, which equals, we were just computed the frequency, 2.26 times 10 to the 15th hertz, divided it by 3.0 times 10 to the 8th meters per second.
And the middle one's on top, the bottom, I can't see. When you divide it, see?
Would you divide f to?
Because you're trying to get that,
What do we C divided by F or F divided by
yeah, see divided by F. 'Cause you would divide
Yep.
it.
Good. Thank you. Good job. because I'm dividing both by frequency like this, right? So C divided by frequency. And when would I have caught that, even if I'm just cruising on and like doing it mindlessly, just writing it down, when would I find that error? When I did my units check, right? When I got to the units, I go, wait a minute, my units are wrong. I've got something wrong in the formula. Go back. Before I invest the time in doing the math, I check the units. Before, I had it inverted, right? I had frequency divided by speed of light. So my units would have been hertz divided by meters per second. See? So my ending units would have been 1 per seconds times seconds per meters, and I would end up with 1 per meters. I'm like, what's a 1 per meter? That doesn't make any sense. Oh, I've got it inverted because I'm looking for meters, right? So I would know right then my formula is upside down. I'm looking for meters, and I ended up with 1 per meters. I'd go back over here and just take my whole math problem and go flip it over, which is in effect what we've done now. We've, rather than frequency divided by speed of light, we now have speed of light divided by frequency. That's going to be 3.0 times 10 to the 8th meters per second, all over 2.26 times 10 to the 15th, 1 per second. I'm going to write it as 1 per second. That's a hertz. You check my units now, it's going to be meters per second times a 1 per second, but I flip it. There's a second per 1, and I'm left with meters, so this setup is right. So now I'll invest the time in actually doing the math. For me, approximation, I've got 3 divided by 2.26, so I'm looking at, if it was 2, I would have 1.5. It's a little less than 1.5. It's probably about 1.43, 1.44, 1.33, okay. Well, so we would have ended up with, 1.33, let's say that. Then let's do the exponents, okay? So we've got times 10 to the 8th divided by times 10 to the 15th. 8, the numerator, 8, minus the denominator. In this case, it's a positive 15, so it stays minus 15. And we end up with approximately 1.33 times 10 to the negative 7th units meters. Okay? So we went from energy to frequency, from frequency to wavelength, 1.33 times 10 to the negative 7th meters. If the problem said in nanometers, what would we do? Okay, so we know it's going to have to look like times 10 to the negative 9th meters, because that is a nanometer. In order for this to become 10 to the negative 9th, we've made it smaller by 2, so we need to make the coefficient larger, moving it by 2. So that'd be 133 times 10 to the negative 9th, or 133 nanometers. Let me check my answer key, see how we did. Boom. Yes, sir.
So how did you know which formula to use at the start of the problem?
I was given energy, and I need a formula where I know all but one of the variables. I know energy. We're always given Planck's constant. I can solve this one for frequency. Was that what we were technically asked for? No. So I need to think, if I can solve for frequency, I can't use this formula for anything, yet. The only equation you have that deals with energy is this one. So you're going to have to use that one in some way. So you'd solve this one.
So we do use that one since it gave us energy.
Yeah. Well, they gave you energy. You know Planck's constant. They asked for wavelength, but you said, you know what? I can't solve for wavelength, but I can solve for frequency. And I know if I have frequency, I can solve for wavelength. Mm-hmm. Yeah, this is the inverse of the way you normally do it. Normally, you're given a frequency to solve for energy, which is straight formula, no real thinking in there, or given a wavelength to solve for energy, which you have to convert wavelength to frequency. Because you'll look at it and go, I'm given wavelength, but I need frequency. Oh, I know how to do that first. And then after doing that first, then computing the energy. In this case, you got to kind of work it backwards. Okay, I've been given the energy. I need the wavelength. I can't solve for wavelength knowing energy, but I can solve for frequency knowing energy. And then once I have the once I have the wavelength, I can solve for frequency, that way. It's the problem, but the logic is backwards.
Can you on those problems where you like find
The electron configuration,
yeah.
both full and abbreviated? Okay, we can do that. If you just need a one-time review of the entire module, I believe video number 8 is the one that you're going to want to watch. 0308. I think that's one day when I just said, let's go from the book, let's just go through the entire module like a rapid review. Okay? So 03.08, if you decide you want to watch that. For those of you that weren't here, I don't want to use names for the video, but if you weren't here for a major portion of material, 0308 is the one I think that is the one period review of the whole module. All right. There are some questions on the exam, and I looked at it this morning for the first time. There are some questions on the exam where I'm going to have to give some clarifying notes to you all, okay? Like, this is what they mean by this question, like a little bit more information. So remind me tomorrow when you're taking the exam. If I don't remember, I may put those notes on a PowerPoint, and have them on the board for you. But tomorrow during the exam, if you're like, I'm not exactly sure what their angle is on this, ask, and I'm going to read through it again while you're taking it to refresh my own memory, make sure I caught them all. Because there are certain ways I said things, and they say it, and I even think the way they say it's a little bit like, I could take it, there's a double meaning in that. I could take it one of two different ways. And so I want to, give you the benefit of the doubt and help you with those. So we've been asked to build an electron configuration. Let's go ahead and build one that involves S's, P's, and D's. Okay? That way we can practice doing a little bit of the D shell or D orbital jumps in our full configuration. So why don't we pick something from the 5th energy level? Let's pick something from right over here. Because I said so. Will's going, why? Oh, number 39. Why? Okay, let's do number 39. Why 39? Because Will said so. No, well, and sweet. I had a hint I was going to give you, and I forgot it already because I'm laughing at this. Okay, let's just go ahead and build the electron configuration for number 39. I don't remember the name of Y, but it's just Y. We're going to build it using the periodic table. Now, the slant chart that I taught you, again, the book doesn't teach that. That's just the way I learned it. For me, that makes sense. If that helps you, great. If it doesn't, you will have a periodic table to use. So build from there. All right, so we're building up to 39. Building up to 39. If, for example, let's say 39, if I wrote it this way, what number would I write on top of it? Well, Y 39, let's 88.9. Let's say I made it 89. 8939, right? You might see it like that. Actually, I think this textbook, don't they have the atomic number on top and the atomic mass below? Okay, so to be consistent, you probably see it like that, right? Okay. Which would look like this, wouldn't it, also? Right, because superscript preceding shows you the mass. Just remember we used these examples. It was carbon 14, carbon 14, or so the preceding superscript, what they're doing is giving you the atomic mass. Why would they bother to give you atomic mass? It's probably a question dealing with isotopes, right? Because every carbon is going to have 6 protons. What they're getting at is how many neutrons do you have? So when you see a question like this or you see it written this way, they're probably asking you an isotope question. Okay. So building the electron configuration using 39 electrons to get to element Y. Let's just go from left to right, top to bottom through the periodic table, using the periodic table as a guide. Remember, helium should be on this side because it has both a 1s1 and a 1s2 electron in that first orbital, the 1s orbital. So we start with 1s. Since it's full, we know it holds 2, and I just say 1 and 2 are both there by including 2. Next energy level, second row, right? Going from left to right. So we've done 1s, 2, it comes from here, 2s, 1 and 2 are both included. So I write the highest one that's included, and this is 2. Then shooting across, we don't have any D's in the middle. We shoot all the way across, and we end up with P's. It's still the 2p, and it can hold 6 total. So the highest address in that block is the 6. Pardon? I'm not there. I did 1s, then we did 2s, 2p. Now we're down to 3s. Okay? So now we're at 3s. Are they both there? Yes. So we had the 3s2. Are there any Ds? No, we shoot all the way across to the p block. Do we need all of them? We do. So let's go ahead and just put the highest one. That'd be 3p6. Okay, 3p6, we've built the configuration. We are now currently, with that electron configuration, we are at argon. We have counted for 18 electrons. Let's make sure. 2, 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. We're at the electron configuration of argon, and we're going to keep building. Now we come over here to potassium. Potassium is the 4s1, calcium is 4s2. Highest one there is 4s2. Now, world goes crazy, right? Because we're at the 4th energy level, but we do have a D block now. Now D comes into the picture. Is it this was 4s, this is not 4D, it's 3D. Whoa, okay. It's 3D because we drop the energy level 1 whenever we're talking about the D orbitals, the D block. Remember to drop the energy level by 1. So it went from 4s, we now go to a D, but it's 1 energy level down from the whatever we're at. Here it's 3, D. Do we need them all? We do, and there's 10 of them, so we're going to go ahead and just note that we have all of them. After the 3D, now we're over here. Now we're back into the P block section. We're out of the Ds, we're into the Ps, so what do we do with our energy level? It goes back to its original. It goes back to the row. So this is going to be 4p. Do we need all 6? We do. Okay, so we're at 4p6. We come back around here. After 4p6, we've got the full electron configuration for krypton. We come back over here. Now we're at rubidium. We need rubidium, strontium. That gives us 5s, 1 and 2. So 5s2 is our highest. And we note that because we needed all of them. And then we go to the next one, which is what we're looking for. We need one more electron. That one more electron is in the D block, which means it's 1 less than this, right? Goes from the 5th, we bring it down 1 to 4, D, 1. And that's the full electron configuration for that element. Now, some of you have made this error, so hang with me even if the bell goes, but you'll be done in just a moment. To write the abbreviated configuration, wherever I'm at on the periodic table, just go all the way to the right and then up 1. We go back to, in this case, krypton, right? Krypton is before rubidium. It's at the 4p6. You see that? Krypton ends with the 4p6 electron. Here's the 4p6. I'm going to note that by putting a bracket around it. And then saying I can rewrite this whole thing in the abbreviated format by replacing the configuration of krypton like this. This signifies this. All right? Now, whatever is not included in the brackets needs to be tagged on here. So 5s2 and 4d1. Some people do this, and it's wrong. It's wrong, okay? They say, whoa, I've got to account for 3 more electrons. That must be the 1s2 and the 2s1. That's wrong. Don't do that. You pick up where you left off.